Hi my dear friends, welcome to Venus EduTech. In this video, we can discuss the last topic of this chapter, real numbers, and that is rational numbers and their decimal expansions. So, we can start the class, right? Yes. Friends, look these examples, 0.375, 0.104, 0.0875 and 23.3408. See, 0.37 can be written as in the P by Q form. How we can write 375 by 1000, right? This can be written as 375 by 1000, which again can be written as 375 by 10 raised to 3 because 10 raised to 3 it is 1000, right? Now going to the next one. This can be written as 104 by 1000, again 1000 in order to remove this decimal, right? Which is equal to 104 divided by 1000, it is 10 cube, right? And again 0.0875, which can be written as 875 divided by not 1000 but it is 10,000, right? Why friends? Because here there are 4 places right after the decimal. So in order to remove the decimal, write 4 zeros in the denominator in order to remove the decimal of the numerator, right? And here also 233408 divided by how many zeros? 4 zeros, right? And here which can be written as expressed as 875 by 10 raised to 4, right? Because 10 raised to 4 it is 10,000. And here also which is equal to 233408 divided by 10 raised to 4. That means all these numbers 0.375, 0.104, 0.0875 and 23.3408, all these numbers can be expressed as rational numbers, right? P by Q form, whose denominators are powers of 10. Look here, in each example the denominator is of the power of 10. 10 raised to 3, 10 raised to 3, 10 raised to 4, again 10 raised to 4. That means whose denominators are powers of 10. Now we can try to cancel the common factors between the numerator and the denominator. These are just examples, okay? So this can be written as, here in the denominator 2 cube into 5 cube, and here it is 5 cube into 3. Why? Do you know why? Because 5 cube it is 125. 125 into 3, what is the answer? 375. Here. And what about 5 cube into 2 cube? 2 cube it is 8, right? 5 cube it is 125. So 125 into 8 it is 1000. So this can be expressed in this form also, right? These are just examples. Okay. So this can be expressed as 3 into 5 cube by 2 cube into 5 cube. And again this one. Here we can cancel 5 cube and 5 cube. So that 3 by 2 cube, which is nothing but 3 by 8, right? Now considering this one, this can be expressed as 2 cube into 5 cube in the denominator, because when we multiply this one, we will get 1000 or 10 raised to 3. And here it is 2 cube into 13, right? We can check it. 2 cube it is 8, 13 into 8 it is 104, and 2 cube into 5 cube we proved that it is 1000, right? And here we can cancel the common factors 2 cube, 2 cube. So that we will get 13 by 5 cube, which is equal to 13 by 5 cube, it is 125, right? Now what about the next one? 875 by 10 raised to 4, which can be written as 2 raised to 4 into 5 raised to 4, right? And here it is 2 raised to, yes, here it is 7 into 5 raised to 4. Right? Not 5 raised to 4, it is 5 cube. We can check it because 5 cube it is 125. And what is 125 into 7? 35, 3, 17, 1, 8, 875. And what about 2 raised to 4 into 5 raised to 4? 2 raised to 4 it is 16, right? And what about 5 raised to 4? 125 into 5, 625, right? And what is 625 into 16? Multiply it so that we will get the answer as 10,000. So 2 raised to 4 into 5 raised to 4 is 10,000, or it can be expressed as 10 raised to 4, right? And here we can cancel the common terms, right? 5 cube and 1 5 get cancelled from here, so that we will get the answer as 7 by 2 raised to 4 into 5, which is equal to 7 by 16 into 5, right? What is 16 into 5? 80. So this can be expressed as 7 by 80. And what about the next one? This can also be expressed in the denominator as 2 raised to 4 into 5 raised to 4, because we just proved that 2 raised to 4 into 5 raised to 4 is 10,000 or 10 raised to 4. And what about the numerator? It is 7 into 521. This can be expressed as 7 into 521 into 2 raised to 6, right? And cancelling the common terms, here 2 raised to 6 becomes 2 square, right? So that we will get 7 into 521 into 4 divided by 5 raised to 4, right? And we can check whether 7 into 521 into 2 raised to 6 is this numerator, right? So 521 into 7, it is 1436. And what about 2 raised to 6? 16 to 4, 64, right? And on multiplying, we will get 25, 2, 12, 14, 40 to 4, 24, 28, 36, 38, 21, right? 8, 10, 14, 13, 3, 2, 3, 3, 4, 0, 8. Yes, it's right. And 10 raised to 4 can be expressed as 2 raised to 4 into 5 raised to 4. So this can be expressed like this, right? And which again can be simplified as 521 into 28. What is the answer? 1, 8, 16, 41, 2, 4, 10, right? So 8, 8, 5, 4, 1, 4, 5, 8, 8. Is it right, friends? 1, 4, 5, 8, 8 divided by, then what about 5 raised to 4? It is 25 into 25, which is 625. So this decimal numbers can be expressed as rational numbers, and then again we cancelled out all the common factors to get this form, right? Again P by Q form, that is rational number form, right? So any real number can be converted into rational number. Understood? So friends, what we can conclude from these 4 examples: any real number whose decimal expansion terminates. This is an example of a real number whose decimal expansion terminates. This is also such an example. This one is also such an example, and this one is also such an example. So any real number whose decimal expansion terminates can be expressed as a rational number of the form P by Q. These are all P by Q form, right? So P by Q where Q not equal to 0 and both P and Q are co-prime, right? Both P and Q are co-prime, Q not equal to 0, and the prime factorization of the denominator gives either the powers of 2 or powers of 5 or both. Understood? The decimal expansion of a real number, any real number whose decimal expansion terminates, can be written in the form P by Q, a rational number of the form P by Q, where Q not equal to 0 and P and Q are co-prime. And the prime factorization of the denominator, the prime factorization of this is numerator and this is denominator, right? And the prime factorization of all these denominators can have either in the form, in the powers of 2 or powers of 5 or both. Either it can be expressed as a power of 2 or a power of 5, or in some cases powers of both 2 and 5. Why? Because the prime factor of 10 is, the prime factors of 10 are only 2 factors, and that is 2 and 5, because 2 into 5 is 10, right? So the prime factors of 10 are only 2 and 5. So we can write either in the form of powers of 2 or in the form of powers of 5 or both. So in general we can say that we are writing in the P by Q form, right? So generally we can say Q, the prime factorization of the denominator Q, can be expressed in the form of powers of 2 raised to n into 5 raised to m. Either in the power of 2 or in the power of 5 or both. So in general we can express the denominator, the prime factorization of the denominator Q as 2 raised to n into 5 raised to m, where n and m are non-negative integers or positive integers. Got it? Once again, here any real number whose decimal expansion terminates can be expressed as a rational number of the form P by Q, where P and Q are co-prime and Q not equal to 0. Q is the denominator, right? And the prime factorization of the denominator or the prime factorization of Q will have the prime factors in the form of powers of either 2 or in the powers of 5 or both in the powers of 2 and 5. Or in general, it can be written in the form 2 raised to n into 5 raised to m, where m and n are non-negative integers or positive integers. So now friends, we can go to the next theorem, that is theorem 1.5 and page number 16 in our textbook. So what the theorem says, the thing we just told right now, right? That is, let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So what the theorem says? Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n m are non-negative integers. So once again, what the theorem says, let x be a rational number whose decimal expansion terminates, right? Then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n m are non-negative integers. So understood this theorem? Once again, let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form, which form? 2 raised to n into 5 raised to m, where n m are non-negative integers. We considered the examples 0.375, 0.104, 0.0875 and 23.3408. So now I just wrote in the reverse form, that is 3 by 8 can be written in like this, because in the earlier case we just written 0.375 into this form, right? And 0.104 of this form, 0.0875 of this form, and 23.3408 of this form. Now we are just reversing the order, that is 3 by 8 can be finally written as 0.375. 13 by 125 can be written as 0.104, like that. Okay. So what does these means? This means any rational number can be written in the form p by q, where q is of the form 2 raised to n into 2 raised to n into 5 raised to m, to an equivalent rational number of the form a by b, where b is a power of 10. Then the decimal expansion of such rational number terminates. So here we are just reversing the order, that is, we are starting from 3 by 8 to 0.375, like that. These 3 examples, that means any rational number can be written in the form p by q, where q is of the form 2 raised to n into 5 raised to m, to an equivalent rational number of the form a by b, where b is a power of 10. Then the decimal expansion of such rational number terminates. Understood? So here comes the next theorem, that is theorem 1.6, page number 16 in our textbook. So what the theorem says, the reverse order of the previous theorem, that is, let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. What was our previous theorem says? What was that theorem? Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers, right? So just reversing that, we will get this theorem, that is, let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Till now we consider those rational numbers whose decimal expansion terminates. Now we can consider the rational numbers whose decimal expansion is non-terminating, repeating or recurring. Right friends? Say 1 by 7. What will happen when we divide 1 by 7? See, 0.0, right? 1, 7. Remainder 3. Again we are putting 0 so as to get 7 4s are 28. Now we are getting the remainder as 2, putting 0, right? Then 2 7s are 14, right? Again the remainder is 6, putting 0, then 8, 56. Now the remainder 4, 0, 5, 35. Now the remainder 5, again putting 0, so that 7 7s are 49. Now the remainder 1, again putting 0. Now again 1, 7, remainder 3, putting 0, 4, like that. That means this rational number 1 by 7, it is of the form p by q, but its decimal expansion is non-terminating repeating. It is not going to terminate, it is repeating, right? That is after the remainders are 3, 2, 6, 4, 5, 1, again 3, like that. That means after a certain stage, the remainders will start repeating, so that we will get a block of digits like this. That is 1 by 7 will be equal to 0.142857, again 14285, again 142, like that. It is repeating. It is not going to terminate. That's why we call those rational numbers whose decimal expansion as non-terminating repeating. What we call it as non-terminating repeating. So there is a theorem which is defined for such rational numbers. This is the theorem for such numbers, that is for such rational numbers whose decimal expansion is non-terminating repeating. And the theorem is 1.7, page number 17 in our textbook. So what the theorem says, let x is equal to p by q be a rational number such that the prime factorization of q is not of the form, mark friends, not is not of the form 2 raised to n into 5 raised to m, where nm are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring. RECURRING, recurring means repeating. Okay, so what was the previous theorem, that is theorem 1.6? Just a slight difference between this and that theorem, that is let x is equal to p by q be a rational number such that the prime factorization of q is of the form. In the previous theorem, it is of the form 2 raised to n, 5 raised to n, right? Then such rational numbers whose decimal expansion terminates. But in this case, the prime factorization of q is not of the form 2 raised to n into 5 raised to m. Then the decimal expansion of such rational number is non-terminating repeating, right? So what the theorem says, once again, let x is equal to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to n into 5 raised to m, where nm are non-negative integers. Then x has a decimal expansion which is non-terminating repeating or recurring. So we studied 3 theorems today related to rational numbers and 2 theorems related to rational numbers whose decimal expansion terminates, right? And 1 theorem related to rational numbers whose decimal expansion which is non-terminating repeating or recurring. So from today's class, what we can conclude, friends, the decimal expansion of every rational number is either terminating or non-terminating repeating. So that's all for today's class. Do exercise 1.4 in our textbook as homework. Just give a try. I will give you the solutions in the next class, because if we do all those questions and solutions in this video, the video will be more lengthy. So to avoid that, we will discuss the questions and answers of this exercise, that is exercise 1.4, in the next class. So if you find this channel, these videos useful and informative, give a like, subscribe the channel and share it with your friends. See you in the next video. Till then, have a good day and thank you.